By the way, hello.
Hello, everyone. Can you hear me?
Yeah.
Yeah.
All right, great. Welcome to ITS 140. Okay, so now today's Thursday, so it's our second time that we're meeting with the class, and today we're gonna basically get started with some of the topics officially. So I've given all the instructions at this point. If you haven't done so already, make sure you take a look at those videos or that video of the introduction. So before I start, let me just quickly take a picture of the people in the class, the roles, so I can register that in. All right. So so let's get started today. So today, usually we do a lab session today, which would pretty much mean that I would start doing examples of code or pseudocode, or just talk about problems in general. But given that today is the first day or the first lab, we haven't really had a chance to cover any of the topics yet. So usually we need to do an introduction of computing as a whole. So today, I'll spend a little bit of time, probably, some time just going over the slides, the first slides. And then the second half, I will kind of go over the Jupyter notebook and really just get, I'll kind of show you how you could use it and then just, a lot of these things with technology, it's like anything, right? You get I'm sure when you first got your first iPhone, right? You didn't know everything about it, so you played with it. You have to play with it, learn things about it. So it's the same with this, right? So today I'm going to just give you, there won't be any homework assignment this week. I'm just going to give you the technology, and then show you some examples of how to use it. I'll just show you a very, very brief introduction to how to, add numbers and things like that. And, basically use it like a calculator in Python. And then after that, I'm going to let you guys play with it. And then starting next week, hopefully on Tuesday, we'll start to get into the actual, programming and things like that. So before I get started, are there any questions?
No.
Okay, great. So there's no questions. So if you have questions later after I do the demo, of the Jupyter notebook and everything, you can also ask then. Okay, so let's get started. So let me bring up the slides. So I have a set of slides, and these slides that I'm using right now, I'm going to change, or not change, I'm going to add another set of slides that ties into the book. I just haven't received those slides yet, but probably by next Tuesday they will be posted as well. But these are fine. These are just an introduction of programming, so there should be fine. So let's see. I'm going to share. The slides. Okay, and I'm going to close. Oops, I'm going to close that. All right, and then you should be seeing them. Right, so these are just basically an introduction. So you guys, you should be seeing the slides right now. Please let me know if there's a problem. And really, today should be pretty easy because we all know what a computer is, right? So we all know what computers are. And really what we're going to define today is what is a program. Okay, so that will be, in general terms, what's a program. All right, so let's go ahead. So as you know, you've been using computers. You're a generation that has always been digital, right? You probably, you have a radio at home, I assume, but you've been a generation that has been entirely digital. And so you're very familiar with computers, okay? And computers just, have changed, our lives basically, right? So they're extremely important. And I think you appreciate that, that you can do amazing things with them. So, you're in this program because you like, IT, and that's really great. And as I said, I always stress, don't get frustrated with programming, take it as a fun thing. It's like, fixing something, building something. Nothing is easy, but nothing is impossible either. And this is not even like a very hard thing. It's just a thing that requires work. Just put in the work, practice. Over the years, you'll get better. In 5 years, 10 years, you're still going to have challenges, right? So, and one thing that's very important that you should be aware of with programming is that programming changes constantly. So it's amazing how certain languages that were very popular in the past are no longer that popular. Other languages are, have taken over. And then there's a few, there's a few languages that stay over the years, like C, C++, for databases, SQL. And so Python probably, because Python is really just an interface to C, C++. And so in that sense, I think I need to admit somebody into it. In that sense, Python is secure because it's really just an interface to C, C++. A lot of the very powerful libraries, another person. So a lot of the very powerful libraries that are written for Python are really C libraries. And so, and hopefully you understand that, you know, there, and we'll talk a little bit about this today, is that in programming, you really just don't really just have like one language and then that language somehow gets processed, right? You have various levels of the language. So what you have is things like interpreters or compilers, and they are devices to take a programming language from a level that's machine readable, right? Something that we understand, and starts converting it into lower level representations. So, you know, until you get to the very low level that the computer computer hardware actually understands. Remember that, you know, the way that you want to think of programming in a computer is that a computer has hardware, has a CPU, a GPU, right? It has these processors. And these processors are like, you know, like extraterrestrials, right? They don't speak your language. They don't really, they are strange. And so you need, between you and these processors, a lot of translators, imagine people that would translate the languages. So you write your language in Python, and then somehow that gets converted into like C binaries, that gets converted into assembly, that gets converted into machine code gets converted into binary, and so on. So there's a whole bunch of representations, okay? And so we'll talk, that's really so what I just said is really what these slides are about. And so that's what I'm going to, you know, what we're going to discuss today, okay? Just, you know, we're going to go through that, kind of to lay that foundation, lay down some of the terminology of programming. And then we're going to start getting into the programming itself. And programming itself is really, as I said, it's really, you know, a set of ideas, I guess, a set of ideas, which we could call pseudocode. And then that set of ideas then needs to convert it into a specific language like C++, JavaScript, PHP, you know, whichever one of those, Python, and, you know, but to convert it into that is again, another translator. So this is like, you know, Python only speaks a certain way of, you know, British English versus American English. All right, and so now you have to, there are certain words that you kind of also have to know, and you have to structure the grammar in a certain way, and they want, you know, and, you know, C++ is obsessed with a semicolon, or, you know, so you have to follow a certain set of rules. You know, that's called a syntax. Anyway, so that's the idea. So let's just start with the slides, just kind of go through them. I think I've given you a big picture. Now let's just kind of go into the details of the slides. So people use computers for school, right? For writing papers, for doing research, email, online classes. Today, you'll start using a new program called, as I said, Jupyter Notebooks. You know, they're very popular. And the reason why I think it's important that you learn Jupyter Notebooks here in 140 is that you're going to see, as you start studying, you know, you're going to, whenever you go online and you look up something in YouTube or a blog or something like that, everyone will always say, oh, and by the way, I have linked my Jupyter Notebook. So, and then you're going to be like, okay, so the code is there, but it's in a Jupyter Notebook. So how do I, and so that's why I think it's very important that you have this as a tool, you know, not just for note taking, which is really what we're going to do today. We're just going to treat the Jupyter Notebook as a notebook, kind of out, you know, the exercise will be for you guys to, you know, this is my notebook for this semester. All right, and so, but yeah, it's important to understand that because you will find, as you start, you know, researching things, you will find your solutions a lot of the time in these Jupyter Notebooks. Okay, so anyway, so, you know, we use it for school. So you're using it for school. Talked about that. You're using it for work, for analyzing data. make presentations. You know, obviously, you know, everyone talks about Excel, but nowadays there's a lot more tools out there than Excel. Okay, we have actually a minor in this program in applied data science, and so that's really, you know, analyzing data. And so we cover a lot of courses. It's very Python heavy, because that's the language of applied data science. So, you know, you definitely use computers for that. And at home, you use it for online shopping. You buy, I'm sure you buy your books online, and, you know, for communicating with your friends, especially now, you know, right now with the situation. And of course, I'm sure a lot of you play video games. All right. All right, and so, and I'm sure there's other ways out there in which you use your computers. So let's, devices that are computers, so as you know, cell phones, iPods, you know, all kinds of things. What are some other devices that are computers as well that you can name, for instance? What do you think? How many of you have a gaming rig that you've built, an actual gaming rig with powerful NVIDIA GPUs? How many of you? Anyone?
I do.
Someone.
I do.
I do.
Yeah. Okay. You have NVIDIA GPUs on it?
Yeah.
GTX, baby.
GTX? Okay. Okay. Good. See, and I bet you don't know that those computers that you have are also very powerful for applied data science. So even though you have them for gaming, you actually have a very powerful computer for other applications. You know, you can actually use that for work, not just for fun. And so, because at the end of the day, when you need to process, as you might imagine, when you need to crunch a lot of numbers and process a lot of data, you know, a GPS, you know, like these gaming consoles, they're very good for also for other tasks like data science. So that's really great. And in the future, there will just be more devices. Everything, you know, the Internet of Things, right? So our refrigerators are going to be computers and everything. Okay, great. Talked about that. Okay, so now, you know, I kind of got framed or put our class into context, right? With computers. Now we'll talk about programming. All right, so computers are designed to do any job that their programs tell them to do. That's where the program comes in. A program is a set of instructions that a computer follows to perform a task. Okay. So in this class, this is your first programming class, so it's meant to be kind of simple. Python is I want you to understand that Python is an extremely powerful scripting language. It's not a compiled language, it's a scripting language. It's extremely powerful, but it's simple and easy to understand. Now, for those of you that are thinking, ooh, I want to build serious applications, you know, for that, eventually you will want to use something probably like C++. And I just want you to know that you will take C++ later. And so then when you take it, you know, you can do all those things. Some of the things that we're going to cover in this class are not, you know, are not specific to C there, because as I said, even though Python is built on top of C, it has another objective, which is really to get you to do something really quickly. I don't know if that makes sense, but you know, what I mean by that is that in C, you want to build you want to declare a variable in C that handles letters. It's going to take you some work, okay? Because you have to define arrays and there's a lot of things. C is a more powerful, faster language, but it just takes more work to get anything done. So imagine if it takes a lot of work just to read a variable. Imagine now if you're building an entire application. It takes a lot of work. So really, when you're building the final program, the final application, you're going to build it in C++. But Python is a scripting language meant, I don't want to say that just for this, but the general idea. It's meant for prototyping. So what that means is that I want to get a solution really fast. So for instance, if you're a system administrator of computer systems, you don't always have to build an application. You just want to automate certain tasks, right? And so there you use a scripting language such as Python. You want to analyze some data. You do the same. You know, you write a program in Python, you quickly get your results of analyzing your data. You want to prototype a model, right? So you want to build an entire complex model, and then you want to try out several models, and you know, really quickly you use Python, because Python has thousands of extremely powerful libraries. Eventually though, you know, so if you're, let's say, working, you know, let's say at Amazon or something like that, they're going to have two teams. They're going to have a research team and they're going to have an engineering team. So the research team, you know, let's say they're trying to build, you know, language processing for Alexa, right? So you guys have heard of Alexa, I'm sure. And so you want to, you know, you want to improve the translation of Alexa. So you speak to Alexa in English, it translates it to another language like Spanish. Okay, so the researchers will probably just go in and write all of their code in Python, right? So they'll create their models or bring in their libraries, they'll test it out, and they'll see that the results are great. Oh, here we go. We got this to work. Once they do that, then, and they've done all the testing and all the analysis quickly with Python, then they're going to talk to the engineering team, and the engineering team then will say, okay, what do we need to do? If it's Alexa, they probably build some kind of a C++ application in the background. So then the engineering team now will start building that same program in C++. Do you guys understand that relationship? Does that make sense? All right, so that's important because, you know, I want you to understand that in programming, it's not about one language, right? It's not about one language. But the great thing about it, and this is a perfect example of how, of this idea of pseudocode, right? It's like you again, going back to Alexa, you had this pseudocode, you had this problem of Alexa translating or finding your movies, or Alexa, you know, buy me a pair of socks, something like that. Those are the things that Amazon wants, right? They want to make money. That's our company. Companies just want to make money, maximize shareholder wealth. And so, so the idea then is, you know, we have a problem, we need to solve it. So they think about things, they create models in their minds, you know, they write it out in flow charts, they start writing pseudocode, you know, of ideas. Then they write the code in Python quickly, prototype it, boom. We use all the libraries. A lot of the libraries we already know are C libraries anyway, so we know how efficient that part's going to be. But the actual writing is simple, right? So that, you know, there's different models of writing code, sequential in the CPU. For those of you that like gaming, have your gaming rigs, you know that programming is different. It's parallel programming. But at the end of the day, they're writing it and prototyping it. That idea that they're created in the Python code is pseudocode. You know, it's basically pseudocode is nothing more than the logic in there, regardless of syntax and programming language. After that, as I said, the researchers then need to collaborate, and usually they know C a little bit, right? They have to know C. They collaborate now with the engineering team. The engineering team is C++ programmers. You know, you got to have a lot, you know, getting started with Python is easy. Getting started with C++ is harder, right? Becoming an expert in C++ takes a lot more work than becoming an expert in Python. In particular, you know, there's a lot of things you have to deal with memory. There's security issues with C++ that you don't have with Python. And so a lot of things. But anyway, at the end of the day, you write your program in Python, and then that pseudocode gets, you explain it to the C++ people. Maybe they just read your Python code, and now they implement it in C. But the same things that you do, like if statements, for loops, the logic, it's all gonna be there. Data structures, it's all gonna be there. You know, dictionaries and lists and so on. All of it is going to be in there. And so that's something that's important, I think, you know, in a program, you know, understanding that idea that pseudocode is important because it's the same thing. You know, I think and one great thing about our program is you're going to take PHP, JavaScript, C++, I think C# also, Python. And so you will see that it's always the same things, always the same solutions, you know, slight syntax differences, obviously, depending on how close you are to the hardware, or, you know, if it's a high level. I think Java also we cover. And so, so that's basically the idea of pseudocode. Okay. Does that make sense, guys? Is that clear? Are there any questions, I should say? Okay, seems like there's no questions. So one thing I want to say, so once I get the other set of slides, you will see 2 sets of slides in every module. One set of slides will have no discussion of Python whatsoever. The other set of slides will have a discussion of Python. It'll be the same idea. And so the reason why I'm going to do it that way is I kind of want to approach programming without a programming language approach, right? And then I also want to approach it from the Python approach. So I want to show you that contrast. So I won't always, let's say, go over every slide of the 2 sets, but I will, you know, but it's your responsibility to read them. But you will see that they're repetitive sometimes. And the only difference is that one is programming language less, and the other one has Python in it. All right, so I wanted to say that. As you know, programs are commonly referred to as software. And you've used a lot of programs, so I'm not going to talk about it. So programmers or software developers are the individuals that create computer software. You guys, right? So you're going to write programs in this class. They have the training and skill to design, create, and test computer programs. And then there's a lot of fields that that computer programs are used in. I have, so, you know, the way I teach the class, you know, I work in applied data science. And so you will see me make a lot of examples and comments of that. However, I don't want you to think that that's the only field. Obviously, there are, you know, video game design, right? So video game design, and, you know, there's that. There's, as I said, Internet of Things. There's security programs that you want to develop. There's web development, right? Web, and you know, web development is one very big piece of this program. And you should, you know, it's something that I really like. It's you know, because it's the internet, right? Everything is on the internet. Think about it. You know, it used to be, for instance, that Windows would focus a lot on creating programs. I don't know if you remember historically, but Bill Gates back in the day, right, created Windows, and then he started selling the CDs for Excel and then Word and all these programs, right? Or games or whatever, PowerPoint. But nowadays, they're actually moving away from that model to the web, so that now you get licenses, and somehow now everything's like web-based, and they really don't even, they're almost to the stage where they don't want you to download a program and have it on your computer, but instead they just want you to, via a browser of some kind, you know, have the application there. And you understand, I mean, because it's business. At the end of the day, as business, they feel that that business model is better for them, right? You know, because nobody can steal their program or copy it. It's just on the web. It's also easier for them to update that way. So there's a lot of advantages. So web development is not just about like building an HTML page, right? So there's a lot to it. There's a lot of power. It's just going to get, the lines are going to be more blurred in the future. Like, am I even on the web right now, or am I on an application? And it all comes down to bandwidth, right? The network and all that power. But anyway, so those are really great things that you guys will be doing. But usually though, I will probably, I will admit right now that I will probably have a tendency to mention a lot of data science. All right, so Hardware and software concepts, physical devices that a computer is made of are referred to as computer hardware. You guys know that, I'm sure. And then the programs that run on a computer are referred to as software. And there's a lot of hardware out there. You have a class 135 where I think when you were in the classroom, I don't know how it's going right now, but you would build a computer. Building computers is fun. You know, if you're building those of you that have built those GPU rigs probably know that. If you get a laptop, you kind of just can't really touch, get in there so much. I would almost say if you're an IT student, get an old computer, get an old computer, like maybe your parents or grandparents, have sitting at home some old computers, just play with them, just get in there, try to get them to start up with the big monitors and everything. And it's the same concepts, right? And it'll give you some insight into the hardware. Another thing that's actually, I would recommend, and is pretty cheap, is just buy a Raspberry Pi. Raspberry Pis, the story goes that they were made because there was a group of people, scientists, etc., who missed the old days when you had to buy a computer and put all the parts together inside and everything. And they were kind of unhappy that the new generation, you guys, were forced to just always, okay, I got the computer, it's a laptop, I can't touch it, And so in a sense, they created this idea of the Raspberry Pi to give that back to you. Okay, and so it's cheap. It's $20, I think, $20 to $50 depending on accessories. But I think just the very plain Raspberry is like around 20. Get it, play with it. It's gonna come with a Linux operating system probably, but it'll give you an opportunity to play around with it at a more hardware level, or like I said, find an old computer from your family and put it together. All right, so anyway, so that's the hardware, the focus of the class. I won't mention hardware that much, except probably for this this set of slides, and then then I will we'll move on to just programming in general. But anyway, I think that pretty much covers it. So hardware is the physical devices that a computer is made of. And all the pieces of hardware nowadays with laptops, everything is pretty much integrated. But that at the heart, you have all these peripherals like the keyboard, monitor, printer, etc. But at the heart of a computer, you have three things, right? What are those three things at the heart of a computer?
CPU,
GPU,
RAM,
yeah. And the hard drive, right? The
hard drive, of course, SSD.
Yeah. Or the SSD, exactly. Nowadays, you can either have an SSD or a hard drive, which an SSD is faster, a little bit more expensive, I think. All right, so that's pretty much hardware. So we talked about the CPU as part of a computer that runs the programs. Now, I actually work with this idea of CPUs and GPUs. And CPUs are sequential in a sense. So they're a bit slower for certain tasks. As you guys know, for gaming, GPUs are much faster because they perform certain operations, usually matrix multiplications, in parallel. That is to say, a CPU has, 12 cores nowadays, 12, 24 cores at most, a really good CPU. GPUs have 4,000 cores, right? But they're not the same kind of cores that, the CPU performs certain tasks, the GPU just performs very specific tasks, right? And they're, math related. But both of these are becoming more and more important for data crunching, right? For AI and analytics and things like that. So the CPU is the part of the computer that runs the programs. Without a CPU, a computer cannot run its software. And so a CPU has a set of instructions, right, that you need to give it in order for it to work. But usually operating systems and programming language that you have on top of that, they need to, you create languages, and then you need what are called compilers, etc., things that will convert what you wrote into the instruction set that the CPU accepts. Okay, like the instruction set is set by the manufacturer, for instance, what are Intel or AMD, for instance, which are, I think, the two dominant CPU companies right now. So running or executing a program is the term used when the computer performs the task that the program tells it to do, right? So you're going to run or execute your program. And so today we'll be running programs. We're going to actually run everything. And eventually, although I'll emphasize Jupyter notebooks in the beginning, I will at some point just show you how to run things like on a terminal in Linux. I'll do a demo of that. Or you can always download any Python editor that you can find out there. They're called IDLEs or things like that for Windows, and run your programs that way. I encourage you to use a lot of tools, okay? I encourage you, even Anaconda itself has its own terminal. It has other ways of running the code, okay? So I want you to play with these tools as much as possible, okay? But, today we'll be running, usually when you run things, there's like a little, write the code and then there's like a button that says run. And so you're gonna run the code, okay? So here is a little bit of history. I like history, but I'm not gonna get into this so much. Hardware and software used to look like that. Or hardware, rather, used to look like that at the top. And then at the bottom, you can see somebody holding a microprocessor, right? Much smaller. The first programmable computers were really large. And the reason for that is that back in the 40s, the computers were made out of these things called vacuum tubes and relays. So these like huge light bulbs and, very mechanical, if you will. And so building a computer was very complex because these things were big, they got really hot. And so, but then something happened in the 50s that changed all of that. Who can tell me what that was? What's the thing that changed all of that, that got us from computers with relays and vacuum tubes to the current computers of today? No one? It's right there in the picture.
Oh, microprocessors?
It is the microprocessor, but the microprocessor was, Roswell, was made possible. That may have been. Maybe it came from aliens. So what happened was in the 50s, a group of scientists at Bell Labs, led by William Shockley, I believe, and William Bratton, I think. There's three people. I forget the other person. But they were working at Bell Labs. If you remember, Bell Labs was the AT&T lab in New Jersey that they did in New York, that they revolutionized. I mean, they created our entire era. So this entire digital era that we live in was invented back then at Bell Labs in the 50s, pretty much. And these scientists, which were part of the solid state physics team at Bell Labs, they started playing with materials like germanium and silicon, and they created what is called a transistor eventually, right? So they created a type of a transistor, and then they perfected it, and then they perfected manufacturing. And then this transistor, this little switch that basically it's like a thing that goes on and off, and then when it's on, it allows current to go through, and then so it's got like 3 terminals. And so this little device, which is tiny, right, revolutionized everything because it did the job of those vacuum tubes and those relays that were huge, but in this tiny, cheap thing. And then other scientists at Silicon Valley, California, and other places, I'm sure, they started putting these little transistors into, someone said, the microprocessor, right? And they started to eventually miniaturize them so much that they got millions of them in there. And then from there on, you know, we have computers, right? So, you know, that's really the amazing thing that happened. That little thing changed everything. All right, so anyway, so just a little bit of history on the hardware there. And just remember that transistor is a switch like on and off, right? And you can have multiple of those switches. So now you can have, you know, a set that where some are on, some are off, and then now they allow current to go through, and so you can use them to represent data. And then came another person, Claude Shannon, also at Bell Labs, and he worked on this idea of the logic. You know, they coined that the term of bit, the bit, right? And so we'll talk a little bit about that as well. But that term bit ties into this idea of the transistor, what that person is holding in his or her hand in the photo. You guys can see the photo, correct? All right, so hardware and software, we mentioned before, is made up of CPU, RAM, a hard drive, SSD, you know, and you know, GPUs and other things, right? Motherboard. So RAM is the main memory, computer's work area, if you will. Why is this relevant to programming? It's relevant because you have to declare variables. And whenever you declare variables, you're placing them in RAM, in memory somewhere. And so that's going to take up space. And so you need to define the size of the variables. Now in Python, mind you, that's not such a big issue, but in general in C, that's a critical issue. And it's a critical issue that actually causes a lot of problems in security because, you know, the program has way too much access to the memory. And that memory holds data, it holds programs, it holds code, and it grabs little pieces of what is in RAM and tries to move them to the processor. And if it grabbed the wrong thing, you know, it could cause problems, right? So it's important. Computers store the program that is running as well as the data. As I just said, it is commonly known as the random access memory. RAM is very important. You know, computers today, I think laptops usually are around 8 gigs of RAM to 16, right? But computers nowadays can have up to, you know, a lot, but, you know, some big GPU computers, for instance, go for 128 gigs, 200 and 256. So they have a lot of RAM, right? And why do they need so much RAM? Because, you know, like going back to your idea of games, right? You know that whenever you're playing a game with a lot of multiplayer people, there's a lot of, you know, everything, all those things in a video game are called meshes. They're basically just coordinates, right, of information that allow the render engine to create things. So imagine storing all that data, right? And you need to move the data quickly so you have it in RAM. And that it says, that's why it says there, data is quickly accessed. RAM is a volatile type of memory. That means you turn off the computer, it goes away. It's used for temporary storage only, and so on. Any questions so far? All right, no questions. So let's go through these. We'll just do like 20 more minutes of this, and then we're going to switch gears to the Jupyter Notebook and just go over that. All right, so secondary storage, you know, hard drives, you know, flash drives, floppies in the past. Like I said, if you're going to build your parents' old computer, probably come across a floppy somewhere. So it's just anything that's external where you store your data. As I said, nowadays you have SSDs and so on. You can see all of those. Input devices, keyboards, mouse. And then output devices will be things like the monitor and the printer, right? So those are still pretty essential, obviously, and haven't changed much. Okay, so go back to software again. So everything a computer does is controlled by software. Two categories, basically, if you could break it up into like system software versus application software. So that's like the OS and then the programs that run on the OS. Or like OSs, and nowadays they've changed the name of applications to the apps, right? So that, that's the new like buzzword. You go to Windows 10 and they got tiles. And I actually got rid of that when that came out. I got rid of that tiles thing and I went back to the original look. I just didn't like it. So you just get used to a certain style and you want to work through that. But anyway, that's kind of the idea. So programs that control and manage the basic operations of a computer are referred to as system software. These include the operating system, which is your Linux, Windows, Mac OS, which is basically built on top of Linux, Android. That's a new one today for phones, and so they're just the software that control the computers. Okay, I like Linux. We'll cover a class 372 when you get to it, where we just look at all Linux, not creating the operating system, but using it. And knowing how to use Linux is a huge tool. It's like now you have this gorilla that you can throw at problems, and so it's really great. There you do take a course in operating systems where you will talk about designing software for operating systems, right? So you'll take that class. I don't remember the number right now, and I think that class uses other programming languages. So there you go. So you can see how we do that a lot. You'll get to see a lot of programming languages, but at the end of the day, they all have the same principles, and that's what's really great about it. Okay, and then there's utility programs, right? And then software development tools that like I guess Jupyter notebooks or compilers, GCC, and so on. All right, so those we won't stress programming for these applications. They're obviously, because they're at the hardware level, they're a little bit more complex, right? Creating drivers is not an easy thing. So our focus will not be on system software so much as it will be on application software. Okay, so you'll be writing a little bit of code, and for little programs, most of them will be like console type of applications, very sequential. But over time, as I said, as you take C, C++, you even take a mobile app development class. I forgot to mention that. That's a 400 level class, I guess. So at that point, you will then learn other skills for that type of environment. You'll see that it's a little bit like web development, actually, which is interesting. All right, so application software programs that people normally spend most of their time running on their computers, word processing, spreadsheets, databases, presentations, right? Data science, games, just all kinds of things. Okay. And web development, I would say the web applications is part of this. Okay. So that just to wrap up then here, as I laid out the hardware part of the class. Okay, so yeah, so let me go back to this. All right, so as we talked about the hardware, now the hardware, of course, is what you need to write programs for. So that basically means that you need to create logic, etc., that's going to create that then needs to be translated into a language that the hardware speaks. So in computers, old data is, or let's just say that this way, all data that is stored in a computer is converted to sequences of zeros and ones. Why is that? Why is it zeros and ones and nothing else? Why is there not a 2 in there or a 3? If you want to speak, maybe turn on your microphone. I may not be able to. Here you go.
So the question is why we only use binary?
Why is old data, so look at this concept here. Old data that is stored in a computer is converted to sequences of zeros and ones. So why is that? Why is it that computers only have zeros and ones?
Because they can only answer yes and no's.
Yes and no, sure. And why is that? As far as why is that? So let's see. Gates can only be on or off. Very good. So somebody said that, right? So it goes back to the idea of the transistor. Remember I mentioned that earlier? So they created this transistor, and that's nothing more than something like a little switch. So that transistor is a little circuit that has voltage in it, and that voltage can either be, you know, it's a voltage, right? So it's a measurement from 0 to 1. How much is the voltage? Well, the voltage is 5 volts, right? You know, that's kind of, let's imagine 5 volts. So if it's less than 2.5 volts, we're going to say that it's what? A 0. And if it's more than 2.5 volts, we're going to say it's a 1. Do you see that? So that's really how they came up with things. At the end of the day, in a computer, everything is just voltage, right? Each one of these little transistors just has a voltage charge, if you will, or of on and off. Best way to think about it is like a switch, right? And so because it fluctuates, the problem is it's never precise. We can't say, oh, today the voltage is 2.7 and always 2.7. It's always a variation of that. It just became easier to say, well, if it's always above or always below this number, right? And there might be some errors there, but it has gotten so precise, obviously, that you don't even see it. But that's really why computers only understand zeros and ones, because physically they're made up, if we want to think about it, of these switches, these transistors. And these transistors hold a voltage charge, and that can be only, you know, it's a measurement, right? So you say, somebody comes in and says, in that pin, what is the voltage? And so you're going to say, oh, it's above 5. So then boom, it's a 1. Oh, it's below it's above 2.5. Oh, it's a 1. Oh, it's below 2.5. Oh, 0. And there you go. And now you have millions of these, right? Millions and millions. I don't know where they are on microprocessors right now, but certainly millions. And so, you know, that's how you represent data, because now in a RAM, for instance, in RAM, which is, you know, the device that we talked about a second ago, that's plugged in. And when it's plugged in and you're doing work and you put things in the memory, all it does is it takes a bank or a set of these switches, right? And to represent some number or some letter or something, some of them are going to be ones, some of them are going to be zeros. Does that make sense, guys? Are there any questions about that idea?
No, we're good.
All right, great. I would recommend, there's a really nice book. You don't need it for this class, but if you're curious and you just want to read something fun to read, there's a book called, it's called How Do It Know? It's not even, you know, it's like a, you know, like a person who's not very educated, right? So the title is How Do It Know? And it's really about how computers work. How do it know? Because it's kind of this idea of the RAM works like this. Oh yeah, but how do it know? You know, and so that's the title. If you want to find something interesting to read and fun, that might be something that you might want to read. And it talks a lot about this, computers in general. All right, so we talked about zeros and ones, the concept. All right, so a computer's memory is divided into tiny storage locations known as bytes, right? And that's relevant. All of this is relevant because we have to declare variables and store them in memory. One byte represents one number. A byte is divided into 8 smaller storage locations known as bits, which are binary digits. As I said, that term bits was coined at Bell Labs by Claude Shannon and a colleague of his when they were developing these ideas of how to use the transistor. Bits are tiny electrical components that can hold either a positive or a negative charge. A positive charge is similar to a switch in the on position. A negative charge is similar to a switch in the off position. Right, and you can see that, imagine those switches, that's a byte, and that represents some data. So we need to have, you know, you can think of a byte as 8 switches, and we need to think of now what programming really is creating these data structures that we can interpret. So now we need to use this idea of these switches as being on and off and create some, so how do we make sense of this? How do we represent numbers with this idea? And so that takes us to this. So now the switches are really just representations of zeros and ones, okay? So let's imagine storing numbers. The positive charge or the on position is represented by a digit 1. The negative charge or the off position of the switch is represented by the digit 0. So imagine in a cable, right? You have a network cable between 2 computers. You're sending information, right? So the first thing you need to do, you have the 2 computers always listening. Computer A wants to communicate with computer B. So what does computer A do? They need to send some kind of signal, something that's agreed on by both computers that tells them, okay, I'm about to send data. All right, and so they'll have some kind of a protocol. Maybe it's going to be a protocol where it's, you know, 3 bytes. They're going to send a sequence of 4 ones followed by sequence of 4 zeros, then 4 ones, 4 zeros, 4 ones, 4 zeros. You do that 3 bytes. So otherwise, everything is random, right? But the computer, the moment it receives that, because it's always looking at every single bit, and the moment it receives that, it's going to say, oh, okay, I'm about to receive data. And then now it's going to pay attention. Somebody wrote something. It's a type of a handshake. A 3-way handshake would be, it's a protocol in networking, right? So that's the TCP protocol. Whenever you want to establish, you have an exchange of packets, but it's the same idea because that exchange of packets gets converted into binary, right? So because it's being sent through the cable. And so yes, it's basically, that's what I'm talking about. Only here, we're only thinking about it at the low level. Somebody wrote something. Okay, so so this is the idea, right? So now you're gonna you've agreed on some protocol. Now you send, now the other computer is listening, and now you send 8 bits. So that those 8 bits that you see there, right? And now what the computer needs to do, the computer knows, okay, I received, you know, a 1, a 0, a 0, 1, 1, 1, you know, because I read the voltage in the line, the cable, and it was above a certain voltage, below a certain voltage. And so I have the sequence. Now the question is, how do you take those zeros and ones and convert them into meaningful things, right? Like letters and computers, and numbers. All right, so as it happens, this is a whole mechanism, right? So this correspondence to the binary numbering system, where all numeric values are written as sequences of zeros and ones. So if you might want to imagine that there's a table or a certain set of tables where on one side you have a column called binary, and then on the other side you have something called decimal or hexadecimal or so on. And basically you have equivalences. Okay, if I get these bits, you know, this binary, then that's equivalent to this decimal and so on. Does that make sense, guys? So that's the idea. And there's actually a little bit of like a math formula for that you can work out. And that's what I'm going to talk about in a second. So each digit in this sequence, right? And it starts from right to left, right? But each digit in a binary number has a value assigned to it. So for instance, the first one you can see here is 2 to the 0. Because it's binary, so you really only have 2 options, 1 and 0, right? If you had 3 options there, like 0, 1, and 2, then it would be 3 to the something, right? Because you'd have 3 options, but here you only have 2. So this is the first position, 2 to the 0. The second position is 2 to the 1. The third position is 2 to the 0. 2 to the 2. The next one is 2 to the 3, 2 to the 4, and the last one is 2 to the 7. You see that. And so now that the computer knows how it got the bits in what sequence, and now it also knows that each one has a position where, after it knows where it started, and now it can calculate, oh, if I'm given these 8 digits, then I can, if I'm given these 8 digits, I can calculate the equivalent number for it. Is that clear, guys? Does that make sense?
Yeah, that was a really good explanation of everything. Because I couldn't fit this class in my schedule. When I was taking in the spring, I was taking 140, and that covers a lot of binary stuff. And the professor's like, "Yeah, you talked about it. Not 140. It's the networking class." And he's like, "Oh, it's, you learn this in 140." And I'm like, I didn't take 140. So now looking at it backwards, it makes a lot more sense now, even though I'm done with the class.
And we're not gonna, I mean, it's not even, I don't know why he said that, because we don't really even cover it that much. I mean, except for today. So, because it's really, this is very much just how the computer does it, how the computer understands, because it only understands zeros and ones. But later on, we're just going to look at programming in general. But certainly, this is an important idea to understand. Okay, so anyway, so that was the idea. Let's look at a little another example. So let's look over here. So storing the numbers, right? So remember that let's keep this idea of 2 computers connected by a cable, exchanging data. So now the computer receives this sequence, right, of bits. Voltage is a little above 2.5 here, so it's a 1. Then these 2 are below 2.5, so there's zeros. Above 2.5, all of these are 1s, and so on, right? So you have the numbers. So now, as I said, somebody worked out a math set of rules that says, okay, binaries convert to decimal this way. And there's an equation for it, a little bit of math there for fun. And you can see that, that this is represented like this. So you can see 2 to the 0, we saw that before, right? What is 2 to the 0?
1.
1, right? And then, 2 to the 4, or 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and so on, right? And so we just have to work that out based on the position, and now we have the equivalent numbers. You see that? We have 1 here. We still have the number 2 here. The problem is that because this is a 0, we basically just multiply times 0, and it goes away. And then here, this one is 2 to the 2 is 4. 4 times 1 is 4, so it stays. Whatever this number is, I can't remember, that number times 0 is 0, so it's not there. This one's 0. And then the last one is 2 to the 7 times 1, and is 128. Do you see that, guys? So that's how it works. That's how computers work. And so once you do that, you just add the numbers, and then you get what it is. So for instance, if we get this binary representation, 1 0 0 1 1 1 0 1, that is equivalent to the number 157. Got it? All right, great. So that's it. I mean, that's binary, as I said, pretty brief, but, interesting stuff. I think I really enjoy whenever I learn these things, also learning about the history, because when I understand the history, I understand, this is how it happened. And that's why I like to tell you, it started with the transistor at Bell Labs, and how all these ideas, it took people years to work these things out. It's not like it was trivial. And now it's just, everything is built on top of that. So it's amazing. Okay, so we worked out that example.
So wait, I have a
Go ahead, please. Go ahead. Yeah.
So it'll be 128. The next one be 64, 32, 16, 8421.
Which one? Sorry. Oh, are you looking at this one below? Right. So if you look at the previous one, every position here, right, from right to left, it's assigned like an index position. So the first one is 0, then this one is 1, 2, 3, 4, 5, 6, 7. You can see that in the exponent of the numbers. You see that?
Yeah, I see it. Cause I was thinking like for 2, 7, it'll always be 128. So, yeah, I got it.
You got it now?
I got it.
Yeah, yeah. And then because you have two options, 0 and 1, it's 2. And so it's 2 to the something based on the position. And so over here, the bit pattern that we got is 1, 0, 0, 1, 1, 1, 0, 1. And so that means these are the numbers, the equivalent of those 2 to the something, right? Over here. And so all you have to do now is, yeah, as you said, this position is always 1, this position is always 2, this position is always 4, and so on. I would say sometimes you can just remember this, but it's better to understand that it comes from this. That's just, you know, my opinion. It just, you know, it's more complete. It's a more complete understanding than just memorizing this. And then all you have to remember is that whenever something is a 1, then you multiply it times the number below. If it's a 0, you multiply it, but it just becomes 0 because anything by times 0 is 0. Yes, good questions. Any other questions, please? All right, we're almost done with this, and then we will be ready for, now, again, why is this relevant? It's relevant because, first of all, this is how computers store data. And second, because this is important when you determine the size of your variables. How many numbers can we represent with 8 bits? How many numbers? Is there a limit? Can I represent 1,000,000 numbers with just 8 bits? Let's say I want to represent 65,000. Can I represent it with 8 bits? 255, very good. Somebody said 255. That's right. Let's see. Somebody just wrote, I don't know what that is. Okay, so basically, what that means is if you have a range, you know, 8 bits of 8 zeros, right? That's the start of the range, to 8 bits of all ones, 8 ones, that's the end of the range. So, and everything in between. And that is 256 combinations, right? So with that, you can represent 256. Obviously, we have numbers that are larger than 256, right? And so for that, we need more bits, right? So if I want to represent a number that's like 60,000, then I would need 2 bytes. They're used for a larger number. You can see that here, right? You can see that here where we have the first 8 bits, but now if we add another byte, now we have a 2-byte storage unit or a 16-bit storage unit. And you can see that now we have combinations from 16 zeros to 16 ones and everything in between, and we can represent a total of about 65,000, but it's the basic principle as before. Okay, so that's kind of the idea. All right, and anyway, we don't really have to stress this too much. We just have to kind of be aware that that's the reason why we, especially like in a language like C++, you have 6 integers, because some integers are very small, some are bigger and bigger and bigger. But when you're building, let's say you're building an application on the Raspberry Pi, right? Or the Arduino Uno, those have very limited memory. And so you can't really waste that memory in very large variables. You really have to think about the data that you will store and then figure out, do I really, you know, for temperature, for instance, do you really need 65,000 values in there? Probably not. Okay, and so on. And obviously, if you're talking about real numbers, you know, like floating point numbers, you need even more because now you have the decimal point and so on. You have to think about that. The last thing I'll say before we move on to the other thing today is how about letters? What about letters? How do you store, because we know that this sequence that you see here is the number 65, but then how do you store letters? Because we can't really store letters. Well, what happens is then you have to create yet another conversion table. You can see it here. It's called the ASCII table, the American Standard Code for Information Interchange. And it's basically then now when you build your program, you say, well, if I get this sequence of bits, first I have to convert it to the decimal, just like we learned with that approach. And then that decimal needs to be converted into a letter. So in the ASCII table, that's really what you have. You have now columns. You have a column of the letter A, and then you have the decimal of that letter, and then you have maybe the hexadecimal of it, and so on. But it's really the same thing, and the binary. Do you guys see that, guys? So your program that you would write, if it's something that interprets letters, now you need to have functions, right? You need to have a function that if you type A, okay, I need to take that A, convert it into a number, a decimal, and then I have to take that decimal and convert it into binary and store it. When I retrieve it, I retrieve the binary, convert it back to decimal, and then through the ASCII table, convert it back to letters and so on. And that's how that works. Okay? All right, and then, it just talks a little bit more. Unicode is just an extension of ASCII. And then we talked about other things. We've talked about this binary, so we spent a lot of time on that. Digital images are composed of tiny dots of color, pixels. Okay. Let's skip that. All right, so to wrap up, to kind of summarize then, a computer's CPU can only understand instructions that are written in machine language. As I said, Intel, AMD, they will create processors, and the processors basically, they have their own set of instructions, commands basically. Let's say X40, XC27, and those are real commands that do very simple things. You write programs that need to be converted into that sequence. That's what this is saying. And the problem is because people find it very difficult to write an entire program in machine language, right? It would be very, very difficult to say, oh yeah, I'm gonna do this. I'm gonna XC20, XC35, it would be very difficult. So you have higher level languages that are more human readable. Okay, and that's why we have so many programming languages. So the CPU, very important, is not a brain, certainly not a brain. It's just a machine, right, that does certain things. It's an electronic device that is designed to do specific things. Here are some of the things that it does. It reads a piece of data from main memory, adding two numbers, subtracting one number from another number, multiplying numbers, dividing one number by another number, moving a piece of data from one memory location to another. That's important. Determining whether one value is equal to another value, right? That's logic, right? Is if this or that. Do this multiple times, compare things, perform operations. That's really what CPUs do. And then we write programs on top of that, and amazingly, we can do the things that we can do. CPUs only understand instructions written in machine language. Machine language instructions are written in ones and zeros. The entire set of instructions that a CPU can execute is known as the CPU's instruction set. And each brand of microprocessors, Intel, AMD, Motorola, has a unique instruction set. Okay. And you can see that there. So basically, you have how a program works is you have the fetch, decode, execute cycle. And this is the term used when the CPU executes the instructions in the program. The cycle consists of fetching, decoding, and executing. So basically, you fetch the next instruction in the program. So there's something called registers. So of CPUs, this is kind of outside the scope of this class, but CPUs have their own memory locations, right? So even the CPU itself has this little 16-bit or whatever memory places. It's got several of those. They're called registers, and the registers basically they're like pointers. They're things that store addresses in memory. So really, the way the CPU is working is it's going to say, okay, I'm here and I need to do something. What do I do? Okay, I'm going to look at register so and so that has an address and that address points to a place in memory. So I go to that place in memory, grab that piece of ones and zeros, and then load it into the CPU to perform the next instruction, and so on. Obviously, whatever is in those areas, in memory, needs to be the right command, right? If it could happen that it gets corrupted, the pointer reads something somewhere else in memory, and that would just be, gibberish, garbage, right? And at that point, the CPU will crash. Okay? So anyway, so that's the idea. So fetch the next instruction, decode the instruction to determine which operation to perform, and then execute. Okay? Questions about that, guys? All right. So from machine language to assembly language, so computers only understand machine language, as I said, pretty much ones and zeros. Machine language, however, would be difficult to write. Assembly language is a level in between, right? So we write something in Python, C, somehow it becomes like assembly language, and then there's a program called the assembler, and that's the program responsible for converting the assembly into machine language, the ones and zeros. So assembly language uses short words that are known as mnemonics. Assembler is used to translate an assembly language program to a machine language. So if you can see that here, it's something like move EAX, which is a register in the CPU, to Z. Add whatever's in EAX, add 2, move Y to EAX, and so forth, right? So that's just, we're not concerned about, you'll never probably use assembly language. People at Intel use it when they build their processors and things like that, because that's what they do, right? Companies like Intel, they don't worry about like the C so much. They'll worry about, okay, if we write this in assembly, will it work? And then other people then develop programming languages. So you might imagine how a language like C or Python needs to somehow take those instructions, put them in assembly, and then the assembler puts them in machine language and so forth. So it's a pipeline of steps that happen in place. But the whole point of this is saying that writing in assembler is too complex, and so you write in higher level programming languages that are way more user-friendly than this. But this is how the pipeline works. Okay. So then that, now we're really done with the hardware part, how things work, and we're back to where we want to be, programming. Assembly language is referred to as a low-level language. We're not concerned with that. We are instead concerned with high-level languages that allow you to create powerful and complex programs without knowing how the CPU works, right? So this is just for your own information, to understand the context and understand what's happening behind the scenes. But you will be using words that are easier to understand. Here's a list of examples of languages. So there's Java, C++, C++, Python, Visual Basic, which has now been displaced quite a bit by C#. Fortran is an old program, but sometimes those systems are still running. Ada was a program that was developed to be very secure. It's a very supposed to be for secure applications, although it's not used so much. I guess in some places they might use it. All right, to me, the very important languages are C++, C++, Python, C#, Java is important. And this list does not include all the web development languages, but just be aware that JavaScript is pretty much a regular programming language, and you will be using that quite a bit. So, and everything that you learn in this class, and in other programming classes will be usable in JavaScript. So you'll see how that works. Are there any other high-level programming languages that you know of, maybe that you have used?
I know of some, mainly because my dad works with automating computer systems. He uses a lot of, he actually uses a lot of Python.
Okay.
Because he mainly just builds the prototypes.
Yeah.
And he's like, it's easy because I don't have to make them look nice. Because I
Yeah.
tried to teach it. I tried to teach him like C++. And he's like, "This is so dumb. I just wanted to do the thing. I don't
Yes.
care about making a menu and stuff." But I know a big one he uses is Ruby.
Okay, Ruby, that's a good example. Ruby is another like Python-like language, yes. Very
Yeah,
good.
he uses the two of them together for his work.
Great,
I
great.
also know of Perl. I'm not quite sure what it does, but I've heard of it.
Perl is like Python too. It's a scripting language. It's just, I find it to be harder to understand.
Yeah, because I asked my dad about it. He's like, we used to use Perl, but then we switched over with
Yes.
upgraded the software and stuff.
Yes, I dislike Perl because of that, because it's just harder. Everything is just harder, and it's very similar to Python. And so, and what happens with Python is that people have embraced it, and now whenever they develop it, let's say, and your dad does something, right? So they develop a library for that area, and now that library is available to everyone. And so that happens a lot with Python, where you end up with just so much support and so many libraries that it just makes your life easier.
Yeah, especially mainly because like what my dad does, there's whole like conventions of a bunch of people that automate. Just, they meet together and they're all talking about this, about working together and everything.
Good, excellent, 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 excellent examples. Thank you. Okay, all right, so I think this is the very last one. So now I think just some keywords that we're gonna be using for this. Keywords for reserved words. That's one of the terms, and that just means a word that you can't use when you're writing a program except to define commands. Right? So you can declare a variable that's the same as, for instance, in Python, whenever you want to print something out, there's something called the print statement. So you can't use the word print to declare a variable. Right? Maybe you can call it print1 or something, but we're going to learn also that whenever you're creating variables and things like that, you should be very, have some logic in how you're declaring your variables. Don't create variables like a, x37, instead you want them to be meaningful, because you're going to read the code and you might work on some code and a month later you have to come back to it and you won't remember what you did. So you really have to write it nicely. So they have specific meaning and purpose in the programming language. Those are reserved words. You have operators that perform various operations on data. I've mentioned the word syntax, and that just means it's a set of rules that must be strictly followed when writing a program. Python doesn't really have that much in terms of syntax rules that are very strict, just a very few ones. C is a very unforgiving language. JavaScript is awful in the sense that you have one misplaced semicolon and everything breaks. And so it varies, but syntax is basically that set of rules. Statements are individual instructions written in a programming language. So this is just terminology that we will learn. And I'll be using, you'll hear me say it. Compilers and interpreters, so this is important. So for instance, C in C++ uses compilers. That means you have to take the program and compile it, convert it into a machine type of code, whereas Python is an interpreted language. So it's not compiled. So let's look at that. So the statements written in a high-level language are called source code, or simply the code. Source code is translated to machine language using a compiler or an interpreter. A syntax error is a mistake, such as a misspelled word, missing punctuation, character, incorrect use of an operator. And so that's the general idea. Right, compilers and interpreters. So a compiler is a program that translates a high-level language program into a separate machine language program. So basically, here's the pipeline. So here, a high-level program, let's say, print hello, and then the compiler is going to take that and convert it into the machine language, binary representation of that. And then that machine language is what's fed into the CPU. So that's how that works. An interpreter is a program that both translates and executes the instructions in high-level language, right? So as I said, Python is meant to be fast. So it's not meant to, oh, I have to compile it and then I'm going to run it. You just run it, so that makes things a little bit easier. So it translates and executes the instructions in a high-level language program. So for instance, here we have the pipeline, this process, you can see you have the high-level language, and you have the interpreter, and then the interpreter converts into the machine language, sends to the CPU, and then back. It's kind of a cycle. All right, so so this will be pretty simple. When we run our code, as I said, there's just going to be a little button, or sometimes you just, if you're on the terminal, you type Python and then the script, and then you run it. That's another thing, by the way. What we're writing in Python, we're going to actually call code, but also a lot of the time you'll hear me call it a script, right? So it's scripting languages, so we're going to just write. And again, the idea with script is just something that's meant to be run fast. You write it, you run it, and that's it. Okay, we've talked, so this just summarizes, we've talked about that, and that's it, right? So we are done with this. As I said, this was just kind of an introduction to the ideas of programming. Next, the next 20 minutes, we will go over just quickly getting started with Anaconda. And then after that, next Tuesday, I will start with the actual programming. So we'll start getting into, I think, variables or something. So it's the very first concept. As I said, I'll have 2 sets of slides, one without Python, one with, just kind of go over both ideas. All right, so let's then do this. So I assume everyone installed Anaconda. It's free, by the way. I got some questions that you have to purchase it or something. You do not have to purchase it. So it should be free. You just go to that website. I put the links in the website that I have for the course. There should be a link there to Anaconda. And then you just install it like any regular Windows. There's a Mac also for those of you that have Mac. I think there was also one for Linux. You don't need to create a VM, by the way, for this class. I added the VM in there just because some people like to play with things, but we're really not going to use Linux this semester here because you really have to know Linux, and so that's not something that I expect you guys to know about at this time. Okay, so so what I would recommend you do with Anaconda is, you've installed it, right? And then after that, create a folder. I usually like to create folders on my desktop. So just create a folder on your desktop and call it, 140, something like that, ITS 140. And that's where you're gonna put all of your materials, okay? So what I'm gonna do is I have a folder, 140. And in that folder, I'm sure you're gonna have a lot of materials, but maybe just create one folder that you call a Jupyter notebook, okay? Or Jupyter, or maybe just call it Jupyter notebooks, right? You can call it that, Jupyter notebooks. So let me see. With this, I don't know how to share. I don't think I can share the actual screen. Are you guys seeing what do you see? Do you see me or do you see the?
You're in ITS 140 with Jupyter notebook.
Okay, so you can actually see my folder.
Yeah.
Yeah.
Excellent. All right, that's what I wanted. All right, great. So as you can, that's what I would recommend. Just create a folder in the desktop, call it Jupyter Notebooks, right? And then in there, you can see I have things in here, right? So I have folders, and just create a new folder. You create new folder, and let's call it, lab 1 for instance, right? So something like that. Right, and then that's where you want to put your Jupyter notebooks, right? Your Jupyter notebook. So what I have here is I already installed Jupyter notebooks, so I have Jupyter notebooks Anaconda 3. So I'm going to click on that. You can also just look for it on your you know, the Windows has a little browser, right? A little browser, you can just type that. So again, you know, did you guys see the name? Jupyter Notebook Anaconda 3?
Yeah.
Okay, great.
So we should like go to Jupyter's website and install the notebook.
You haven't installed Anaconda yet? Okay, so if you haven't, all right, so we discussed on Tuesday that you have to install Anaconda. So you have to go to the course website, click on that. And then are you guys seeing my website right now?
Yeah.
Okay.
Yeah.
And okay, if you download to lab environment, there's a little thing here called Anaconda. Click on that. And then you can scroll all the way down and you can see Anaconda installers. Just click the Windows one if you're on Windows. Make sense?
Yeah.
Yeah, and that's just going to give you the wizard, and then it's pretty straightforward. Once it is installed, then what I did is I just go to start, and you can see if you want, you could try Spider if you'd like, you know, but today I'm just trying the Jupyter Notebook Anaconda 3. I opened that, and when I clicked on it, it basically opened this, like on the browser, it opened a website. Do you see it? Yes.
Yes.
Okay, great. So this browser is, if you notice, it says localhost 8888. What that means is that when you created a Jupyter Notebook, right? Anaconda creates a daemon. A daemon is like a program running in the background. And that program is listening on port 8888. And so now when you go to the browser and you type localhost, which basically means this computer, and you type 8888, you're able to connect to that daemon, and now you have access to all of this. Okay, make sense? All right, then I'm going to navigate. As you can see, this has my entire directory structure, so I'm just going to click on desktop, and then I'm going to click on ITS 140, which is what I have here, Jupyter Notebooks, right, and you can see that there. And so now you will be able to access your Jupyter Notebooks, right? So I have, you know, let's say example 1, right? That's a Jupyter Notebook that, you know, I created, or 2, and so on. So I can click on lab 1, for instance. There's nothing there, right, at this time. But that's where we want to save things. So if I'm in 140 over here, lab 1, you can see there's nothing there at this time. But now, oops, sorry. Now I'm going to go over here and I can click on new, and I'm just going to say Python 3. And there you go. This is your very first Jupyter Notebook. Okay, your very first Jupyter Notebook. So let's go ahead and, you know, let me just describe it a little bit. It's like an editor, but you can also write, you know, you can treat it as your notebook for taking notes in the class, if you'd like. I mean, you don't have to. But as I said, the importance of this is that as you start looking over in the internet for code and things like that, you're going to find more and more people saying, here's the explanation. Oh, and here's the link to the Jupyter Notebook. And so, you know, you kind of need to get with what everyone else is doing. All right, so what does this have? It's basically like a browser type of thing, but it can see it's got button. We've got save button, right? We've got insert cell, cut selected cells. Here's an important button, the run button, right? This is the button that we're going to click on or hit every time that we want to run some code, or actually render some text, right? You know, because we're going to be writing some text as well. You know, that's why it's called a Jupyter Notebook. And then it's got the menu. You can, you know, play around with that. That's really my recommendation. Notice we're writing in Python 3. Okay, so don't worry about, you know, I'm just going to throw in some syntax kind of just to demo how this works. We'll talk about all of this later, of course, but let's just say, you know, usually whenever you write a program, I'm sure you've seen, you always do something like hello world, right? So hello or we could say hello Jupyter, right? So all I did here is in these boxes, right? These little boxes where it says in like this, that's where you write your code, okay? So I could write more code here or less code, you know, however I want to do it. And then when you hit run, you can see it actually ran because this is the syntax of Python over here. This is the syntax. And then when I ran the code, it gave me this. This is the rendered output. So it's like in a console program, this is what you would get as output. Does that make sense, guys?
Yeah.
All right, great. Are there any questions so far?
It's not really a question, but it's a comment to anyone that's running the Jupyter notebook. At least for me,
Yes. You cut out. Are you still there?
oh, I
Yeah, I
accidentally I have push to talk on and I accidentally released it.
Oh, okay.
But it's just a for those running Jupyter notebook, at least for I hadn't ran it before. It took a while for it to load.
Okay. But it loaded eventually?
Yeah, it said it was like I'll pull it up. Just it said that it was like generating a secret code and stuff, and that took a little bit. But it eventually opened, and I'm getting the same screen that you're
Thank
getting,
you.
so it's all
Okay.
good.
Great.
I was I was very confused for a while. I'm like, I'll let you keep talking, but I'm like, did I break something? Because I was trying to I was messing around yesterday because I already had it installed. I was messing around with all the folders, and I'm like, I don't know where anything is. I don't understand this.
Yeah, no, I
yeah.
get that. And you know, we'll get used to it. I mean, you know, it's like with everything.
Yeah, because I'm used to Visual Studio and stuff where it's all packaged nicely and it's very obvious where the executable is to actually be able to type your code in. I'm like, where can I even start typing code in? I couldn't even find that.
Yeah, right. No, exactly. So I want you to understand, as I've said many times, this is one thing that we're gonna do using the Jupyter Notebook. We will also just open an editor, type pure code in it, and then run it. Okay, so that's also, those are usually called IDLEs. You open a program, it's an editor, you write the code there, hit run, done. Okay, so there's various other ways, but this is important. Okay, and I think, you know, you'll find it that you can actually put your notes in here, and so it'll help you. So, but this is just one of many tools that we will use. Okay, so so in the time that I have left, so now I've created a hello world. Let me do something else. I'm gonna do A equal, notice that I don't have to declare variables or anything like that. I'm just gonna do 5 plus 2. You see that? And then when I hit run, it ran, but no errors because it didn't say that it didn't like it, but nothing happened. Why do you think that is?
Because you don't have any outputs or any print statements declared.
Exactly. So I still have to print it, right? So I still have to print it. And so I'm going to do print A, right? And then now, if I run it, you can see I have my answer 7. So that's what's so great about this is that, you know, when you're writing your reports and you're doing calculations or you're doing labs, you know, it's going to show the output there and you can document everything really well. So then you can just take a screenshot of this, you know, that kind of thing. And for your own reference, let's say that you built something and now you just want to change it a little bit, you know, you can always go ahead and try to do that. Make sense? Guys, make sense?
Yeah.
Yeah.
All right, so now let's go ahead and try to save the file. So I'm just going to click on File, Save As. And I'm going to save it in Lab 1, and I'm just going to call it Hello World. Okay, so I'm going to call it Hello World. and I'm gonna hit save. Okay, so I've saved it, gave it that name. Okay, now I'm going to, let's say, close it. I'm gonna close everything. Close this. Notice that in my folder, Jupyter Notebook, I have lab 1. Hello World is there, right? Which is the file I created. There's other files, but there's Hello World. And now I'm gonna go and look for it. So I'm gonna repeat the process. I'm gonna go to Jupyter Notebook and I count to 3. All right, I'm gonna go to desktop. I'm gonna go to ITS 140, my Jupyter Notebooks, Lab 1, and I'm gonna click on Hello World. And there it is. Do you see that? So that's, that's basically the process. You create a Jupyter Notebook, you work on it, you save it in your folder, go to your next class. Then the next day you want to work on your homework assignment. And so you load it up again and you keep working on it. Does that make sense, guys?
Yeah.
Yep.
Okay, all right, good. Let's try another one. So let's see, B equal hello Jupyter. Okay. And then I'm going to try print B. Okay, I'm going to hit run. And there it is, hello Jupyter. So now I was able to run my example. Okay. So, we have 2 minutes. So just the last thing. So Jupyter Notebook supports a type of writing language called the Markdown. It is a simple way of creating nice-looking documents with a small number of commands to remember. This language is particularly good for typesetting mathematical equations or just, for writing your own comments, seeing the output, etc. So to write text, as you know, whenever you first open your Jupyter Notebook, you will be greeted with this little box, right? So that's the box that you have seen where you can write your code. But if you want to use the notebook for writing, then you need a different box, which is going to be called the text box, as opposed to the code box. So to do that, we basically have to change the cell. All right, so we will have to go to the menu over here, click on cell. Okay, and then you're going to select cell type, and you can click Markdown. And you see that the text box changed, right? It's a little bit different now. So you'll notice that the square bracket to the left of the cell has disappeared. So meaning we now have a text box to write in. Right? There's also shortcuts and things like that, but that's basically the general idea. So let's just say, this is my note. No, sorry, let's just say these are my notes from ITS 40, something like that, right? So you do that, and then so you have it there in the box, but you still have to render it to the page. So that's the thing you want to do next in order to see what the finished product will look like. So we can try clicking on run, and you can see there, right? So these are my notes from ITS 140. So now any text, so if you notice, that was not, so I should stress, I guess, I didn't, that what I wrote there was not Python code, right? What I wrote there was just text that I wanted to put in there as note because I wanted to explain, oh, by the way, I'm doing this way and that. So whenever you do your homework assignments, for instance, you could use this to explain to me, okay, this is my code, this was my output, and then put my little text, you know, I used this because of this and that. Does that make sense, guys?
Yeah,
Yeah.
it makes sense.
Okay, great. That's really it for now. I mean, I just wanted to give you a quick intro. I wanted to, if you notice, the cell became Python again, right? So the cell became, you know, say 7 times 2. And it printed. And there you go, 14. So you can see, you know, you're building on top of it, and then, you know, just don't forget save as. Definitely one thing that I notice with students always is they write something and they forget where they put it. And then they can't find their files. That's a very common thing that happens all the time. So that's why make sure, create a folder on your desktop, call it My Jupyter Notebooks or something, and then put your files there, give it names that are clear. Practice this a lot, you know, practice just saving that a lot, okay? In another class, we're out of time today, but in another class, we will explore how to use, you know, some other IDLEs and how that would work, right? And we'll be moving back and forth with that. Okay, so you're, nothing to submit this week, but your homework assignment for this week, just for your own, is practice this, okay? Master it. You know, try other Python examples, running it, and get to know your Jupyter Notebook. And then, as I said, on Tuesday, I will begin with the very first topic of programming. As I said, 2 sets of slides, one with just like pseudocode and one with Python. All right, are there any questions before we sign off? All right, seems like no questions. So we're gonna stop here for today, and I will see you guys on Tuesday. Have a nice weekend and welcome.